All right, so today what I'd like to do is continue on with our look at hypothesis testing. And we'll be doing some more practice problems essentially and looking at what's called a p-value method of determining, again, whether a claim is true or false, right? This is such an important part of science and just everyday life is, what information can we trust? And even more importantly is how are scientific conclusions being reached, right? We hear a lot of things being thrown around as, scientific truth or scientific fact, but very rarely do people actually look at how they came up with those conclusions. And so those are the techniques that we're learning is when you publish something in a scientific paper, there are people out there that are looking at the significance of your results. In other words, the statistical validity of your statements. That's what makes it science, and that's what gets it published in these journals, these peer-reviewed journals. So it's arguable that what we are doing right now is the foundation of scientific progress. And these are the steps that I'm going to be looking for on quiz number 3 and 4 and the final exam when you have to do a hypothesis test. I think I mentioned this before, but the multiple choice style of question is going to be slowly disappearing as we progress through the last few chapters of the course. And that's because we want to make sure that you actually understand the process you're going through. And so these are the 8 steps that I'll be looking for when you are doing a chapter 8 problem. And so even though when you're practicing on Pearson, the assigned homework problems are still just kind of, asking for specific things, you should, when you're solving it, you should try and go through these 8 steps each time. You'll get the right answers that they're looking for, but this is what I'm going to be asking for you to submit. Let's take a look at something like question 1. And the reason I want to do this again is because this is going to be very similar to lab number 4, right? Where that project that we'll be working on here over the last month, where I want you to conduct a simple experiment, where you're using that pendulum that you built, and you'll be collecting data. And so it'll look something like this, right? Your data obviously will be different, but you get raw data. So it says 12 different video games showing alcohol use were observed. The duration times of alcohol use were recorded. So I guess these are seconds. Here, test the claim that the sample is from a population with a mean greater than 90 seconds. This is where I took it from. Page 424 here. So I don't know why it creates the PDF and it bad formatting. They would lose a mark if they were submitting that to me, right? You know how I'm tough on formatting. They're saying test the claim. That's the important part. You're going to see that as soon as you say test the claim, it's a chapter 8 problem. So step 1 in all of these things is and so they want to test the claim that it's from a population with a mean, so that's important, greater than, that's important, 90 seconds. And as soon as you see greater than 90 seconds, this, by definition, is going to be the alternative hypothesis, right? As soon as somebody says test that it's greater than 90, I assume that there's some sort of industry standard where 90 seconds is something that you're allowed to have, or you're allowed to show 90 seconds of violence or alcohol or whatever this is. And they say test the claim that it's greater than 90. So as soon as you see greater, that's the alternative. You'll recall from the last video, or this first video, that the null hypothesis, which is the one with the 0, the null hypothesis is always something that equals something. And again, this is kind of the idea that if somebody says test that is greater than 90, the status quo, or the, again, the null hypothesis, the disbeliever, the skeptic would say, you know what, I guess it's, if the standard is 90, it's 90. Why would it be more than 90? Can you prove that the average is more than 90? So again, it doesn't matter which one you state first, as long as you have these symbols in here. In fact, there should be one more thing. I need to put it's the average is greater than that, right? So again, I usually actually pick up the alternative hypothesis first myself, and then that allows me to easily create the null hypothesis because it's just going to be equal to whatever they said. There's two methods. There's the traditional method that I talked about last time, or there's the p-value method. And I'll explore the p-value method today. But both of them involve finding what's called a test statistic first, or at some point. I think last time I did the critical score first, but that's okay. It doesn't really matter what order you do them in. So the test statistic found in your formula sheet, right? These are the three formulas. Remember, there's three types of problems. Same thing as chapter 7. Do you know the standard deviation? Do you not know the standard deviation? Or is it a proportion problem? And in this case, we don't know it, right? They usually, when they give you raw data like this, it means that we have to calculate the sample standard deviation, because they don't give us the population one, which is, again, that's the more common situation. Same thing with your pendulum problem, right? You're going to be doing a t-score test on that lab number 4. Maybe I should spell statistic properly. So in this case, because this is unknown, we are going to use t equals it's basically the same equation as the central limits theorem z-score thing. But we're going to calculate these two using Excel, or your calculator, but let's use Excel because that's more exciting. The average that we'll say is going to be 90. So somewhere in the world, they're saying that the average is actually 90 seconds. So that's what we'll use for the average. The sample size we know, right? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So again, let's use Excel. Let's call that step 3 to calculate our statistics that we're going to use. So if you write that down on your test, I'm going to be like, perfect. Then you're going to attach some sort of spreadsheet where you've entered the data. You always want to double check, that if I made an entry error here, that would be called a non-sampling error, right? That's just me being sloppy. So you always just kind of want to double check that your numbers look good. Your sample size is the same, right? 12 looks good to me so far. And now I can just work with this and easily calculate the mean and the standard deviation. That's quite the high standard deviation. But again, if you sorted this value, right, if you sorted this, there is quite a huge disparity here. So it's believable, but you know, the median is going to be, what's the median on this thing? It's heavily positively skewed, right? The average is much bigger than the median, but that makes sense. I mean, these values are ridiculous, right? This must be a game about drinking alcohol, but that's besides the point. Okay, so here we have our standard deviation, here we have our mean, and you can go back to your sheet now. And now we have all the things we need to get our test statistic. All right, now we're well on our way. So now we can calculate our test statistic. So it does look higher, right? The average is 106.25. The average is just 90. So it looks higher. But again, as we learned last class, that could just be a false positive, right? It could be that this is just a statistical error and, you know, it's not actually higher. So the t-score is 0.3425, 0.3425. So that's pretty low. Now, according to the traditional method, the one we did last time, and let's just do that for now, and then I'll show you the p-score in a minute. But once we have the test score, the traditional method says, well, what's going to be the critical score? And then you figure out which one's bigger or smaller. Now, in order to figure out the critical score, so let's do that. Let's figure out the critical t-score. Again, this is the traditional method. And again, I'm not going to tell you which one to use. You can use either way. This is the one that I used for years because I liked it the most. I found it the most straightforward because now all you have to do is at this point, draw yourself a little graph. Okay, I want to see this because it shows you that this is a one-tailed test, right? If we go back over here, this is a one-tail, what's called a one-tailed test because we're just looking for being greater than 90 seconds. If it said is not 90 seconds, then it would be what's called a two-tail. But because it's a one-tail, it means that all of the uncertainty is over here. All of the uncertainty, in other words, we're just looking for values that might not be high enough. The question is the average that we have 106 found over here or over here? And it kind of makes this line in the sand to say it has to be different enough from the average so that it's not, so that we're confident it's not a false positive. Now, the other thing that you'll notice, the other reason I picked this question, the reason I like it, is because they don't actually give a critical value, right? They give you all the information. 12 games or 12 video games are shown where alcohol is used. What requirements must be satisfied to test the claim? The sample is from a population with a mean greater than 90. Well, first of all, we don't really know what the alpha value is, right? We don't have a level of significance. So when we're not given that, and you'll see that in the flow chart as well, when you don't know, right, this is not specified in the question, and this happens all the time. Usually it's up to the experimenter to do it themselves. And so you can assume, let's therefore use 0.05. This is the same thing as a 95% confidence. The other thing we need to know is degree of freedom, right? That's how we figure out the critical t-score always comes from the chart. Either your z-score chart or your t-score chart finds your critical value, always from your tables. So your degree of freedom in this case, because that's what you need for t-scores, for those of you that have been keeping up with the news or the homework. So that's going to be 11 in this case. And so we would go to our formula sheet, look up our t-scores, right? This is a one-tail test, alpha 0.05, and degree of freedom of 11. So our critical score is 1.796. Okay, so that's this value here, your critical score. This is our test score. It's very weak, right? 0.34 is what we get when we do the math based off the sample statistics. And so therefore that value is over here, right? It's going to be over here, right? If this is 1.76 on your curve, then 0.3 or whatever it is going to be over here, right? That's this point here. This is your test score. It's not in the rejection zone, right? It's not in that touchdown. There's no rejection that happens here, right? This is the rejection zone. And it doesn't make it. The rejection zone is the one we say, well, it's statistically far enough away from the average of 90 that this is too close, especially with that huge standard deviation that we had over there, right? That probably contributed a lot to it. And so your decision, right, or your answer here is because the test score is less than the critical score, we fail to reject the null hypothesis. It could be just out of luck. It could be that it was just you picked. It could be that through your randomization process, you happen to have picked extremely graphic video games where they use a lot of alcohol, right? And that makes sense, right? When you go back and look at this raw data, this does not look like a random video game. This looks like a video game about a guy in a bar, right? It looks like Leisure Suit Larry. And so it's not random in that case, really, right? You happen to have picked a real outlier. And again, please, this is the most important part that I'll be looking for is, and they mention that in the flow chart, is restate your conclusion in non-technical terms. So you have to kind of go back and remind yourself of what you did, right? You said, basically, we're looking at the amount of alcohol. So you can say, there is not enough evidence to show that the amount of drinking time is greater than 90 seconds, right? That's the one that you would publish in a newspaper, or that's the one you would talk to your boss about, or whatever it is, right? And so again, I didn't quite do all 8 steps, but I kind of condensed things into, this is fine if you do it like this, obviously, because that's the way I showed you to do it. This is fine, you know, let's say 6 steps. So identify the claim, I did that. And so I condensed the first two. And the third one. I think I did 1, 2, 3 altogether. Significance level, but I did all of this stuff, right? So again, if you condense this, as long as you have all of this included, I don't really care, but have it so it's laid out for me so that I can give you marks, as many marks as possible. Okay, now let's look at the p-value. So I did this what's called they call it the critical value method. They also talk about it as the traditional method, so it might be a little confusing, but we did the one on the left here, on the right. We did what's called the critical value or the traditional method of hypothesis testing. So let's do this other thing they talk about, because you'll see it in publications and you'll see it in the industry. You'll see it maybe on the quizzes. But again, I'm not really, as long as you do one of these properly, I'll be happy. But let me show you the p-value method, because maybe you prefer it yourself. So the p-value method, all it says here is that instead of looking up the critical t-score, we do everything the same, except at this point here, we make a slight deviation. So instead of going to the critical t-score area, we're going to look up what area of the curve does this correspond to, right? So in other words, we're going to figure out, so there still is a graph that needs to be drawn, but we want to figure out what is this area of a t-score of 0.3425. And then we're going to compare it to the alpha value here to 0.05, basically. So we're going to say, so let me just do one thing first. So you take your t-score, and now you figure out the area under that curve to the right of that. Now with t-scores, it's a little bit confusing because our chart is not that good, right? With the z-score, it's easy, right? The z-score, you would just look up 0.34, right? It's approximately 0.34, right? That's how we rate our z-score chart, just to 2 decimals. So it's quite simple. But you'll notice with the t-score chart, it's a little bit more confusing. I have to look up some value of 0.34 here, and it's not good, right? Because you kind of have to like reverse engineer your, this value here, and so it's counterintuitive. So let's use Excel. This is another example of where Excel comes into play. So here, definitely the traditional method is preferable in this kind of situation. But again, the p-value method says, what is the area here? And we can just use the t-score function of Excel to do that. So I can show you that here, right? So let's go, what happens if I go this one? Returns the right-tailed. This sounds about right. Okay, let's try this out. Let's say I have a value of 0.34. That should be good enough. And then degrees of freedom, that was 11. See what happens here. So this is giving me the area to the right of the tail of a t-score of 0.34 and 11 degrees of freedom. That makes sense. And the value makes sense. So here we have basically 0.37 is right here. That's the area to the right of this value. So how did I do that? I went T inverse, right tail, degrees of freedom 11, and then you're in business. Now, this tells us the area here. Now, the p-value method says all I have to do now is decide which one is bigger. In order to make my conclusion with the p-value method, all I have to do is, in other words, your answer, you're ready to go here. What you have to do is you have to compare this p-value. This is called the p-value to the alpha value. right? And we decided that the alpha we're going to use, right? The alpha value, well, in this case, it was 0.05. Now, again, this is why some people find this a little bit confusing. Here in this case, if your p-value is bigger than the alpha value, it's not good, right? Basically, it's just saying that this area here is bigger than this area, so it doesn't meet the same criteria. I'll clarify this in a second. Because the p-value that you calculate, in other words, this is what is calculated from your sample, is bigger or is greater than the alpha, we fail to reject the null hypothesis. So it's the same conclusion. All right. Now, again, what the p-value gives you, just one more, the reason I like doing this method, and the reason this has grown on me, again, why am I introducing this? Because it's kind of confusing because it's a little bit of the opposite of this method. The reason I like it is the p-value gives you the probability that this just happened by chance. There's a 37% probability that this is due to sampling error. Whereas in order to pass the test, there has to be a 5% chance or less that this occurred randomly. So the p-value gives you, right? And again, that's one of the advantages. When you calculate your p-value, you can say to yourself, what is the chance that this just happened randomly? Whereas you don't get that with the traditional method. The traditional method is like either yes or no. But when you do the p-value, you actually figure out an added piece of information, which is the 37% chance that it's random. So the advantage of the p-value, right? Again, the p-value gives you the probability of a false positive, essentially. In this case, of a false positive. In other words, the likelihood your results are not valid are due to chance. And when you do a 95% hypothesis test, what you're saying is I want to have a 5% or less chance that this was just random, that it was just a fluctuation, that it was not due to actual, you know, it doesn't reflect the true population. But a comparison of both methods here. When you're doing the traditional or the critical score method, right? If your test score, right, is greater than the critical score, you reject the null hypothesis. In other words, that means that your sample is good, your sample data is good, and it shows that something is increased or decreased or changed or whatever it may be. With the p-value method, again, the reason it's confusing is because it's the opposite. If the p-value, in other words, your test score, right, from the sample data is greater than the critical score, then the alpha value, that's also given by the, it's the same thing as critical score. That's the analogy there. You do not reject, you fail to reject the null hypothesis. And so that's the, right, if here you do reject, if this is greater than that, then you fail to reject. And so that is confusing when you first learn about it. You want a small p-value. I guess that's another way of kind of making a conclusion here. We've reached the end of our class period here. So in conclusion, when you're doing your experiments as the experimenter, right? When you're doing your capstone projects or you're doing your lab number 4, whatever it may be, as you go through life, as a scientist doing an experiment, you want, if you're the one doing the experiment, you want to prove something. You want a big t-score, a big t-score, but a small p-value. So in publications, they often report the p-value. So if somebody says, oh, our p-value is 0.0001, that's really good. If you get a t-score of, when you do your sample statistic there, and you get a t-score of like 5, that's really good. So again, you want small p or big T. So you have to wait a while.